Hi everyone. So today we will be talking about the next topic, which is all about work, no, related problems in integral calculus. So before we go on to integrating some of problems in work, we are going to derive or we're going to uh, learn some example first on the basics in work. So example for number 1, how much work is required to lift a 5 kilograms book, sorry, that's 5 kilograms, 2 meters above the ground, and how much work is required to lift a 30 pounds box 4 feet off the ground. So remember that work in physics, we know that work formula is the force times the distance. If we talk about the axis, no, the distance, if it's on the x-axis, is the distance, whereas if we talk about y-axis, it's the gravitational uh, distance, no. So that's the y-axis. So force is equal to mass times acceleration. Once again, acceleration if it's going to that side, and if it's gravitational pull if it's going to this side, so the y-axis. So force is equal to mass times the gravitational pull or push, no? So therefore, if we have this formula where a force is equal to mass times the gravitational force, therefore we can have the formula of the work as mg times the distance. Okay, in which in this problem the given mass is 5 kilograms. Okay, we're going to solve A. So this is A and this is B. So how much work is required to lift a 5 kilograms book 2 meters high above the ground? So 2 meters high above the ground, therefore 2 meters is our distance high above the ground. So that would be 5 kilograms. Okay, remember that the gravity or the gravitational force, that's 9.80665 meters per second or 9.81 meters per second squared, multiplied by its distance, which is 2 meters. So you have work as, if you use your calculator, that's approximately 98.1, wait, times 2. It's 98.1 kilogram meter squared over second squared, or this unit here is a unit of work which is also equivalent to joules. Okay, now for letter B, how much work is required to lift a 30 pounds box off the ground? So to lift 30 pounds box now off the ground, so how much work is required? So for B, we still have the same formula. That's work is equals to, or is equal to, force times distance. We already have the force, no, which is the 30 pounds, and the distance, which is 4 feet. Okay, so therefore this is 30 pounds times 4 feet, which is work is equal to 120 foot-pounds, in which foot-pounds is another unit of work. So let's move on to the next examples. For number 2, find the work done in pushing a car a distance of 15 meters with a constant force of 500 Newton. So constant force of 500 Newton. So the given for problem number 2 is we have the force as 500 newtons and the distance, which is 15 meters. So you have the unit for work here as Newton dash meters, or that's just equivalent to joules. Okay, so work is equal to force times distance. That's W is equal to 500 newtons times 15 meters, which is exactly equal to 7,500 Newton per meters, or Newton meters, or that's 7,500 joules. Okay, now let's talk about integral calculus. So for this example, we have a variable force, which is in Newton, acting in an object is represented by the function f of x is equal to x squared minus 4x plus 7, where x is the distance in meters from the origin. How much work is required to move the object from x is equal to 1 to x is equal to 4. So let's say, for example, this is an object, and the object is starting to, or the object is to be moved from this point, so from x is equal to 1, going to x is equal to 4. Now the question is, how much work is required to move the object? So the work done by a variable force is defined as work is equal to, from A to B, force in terms of x dx. Okay, so therefore we can substitute here the limits from 1 to 4, then f of x, which is x squared minus 4x plus 7 dx. Okay, so integrating that function, we have x cubed over 3 minus 4x squared over 2, or 2x squared plus 7x from 1 to 4. Therefore, that's 4 cubed over 3 minus 2 times 4 squared plus 7 times 4 minus 1/3 minus 2 plus 7. Okay, so that would be, hold on, seven times 4, this is, oh, plus okay, this is equivalent to 12 newtons. Okay, why newtons? Because it's stated here in the problem that there's a variable force which is in Newton, and Newton is a unit of a work. So therefore, that's our final, joules pala, no? Newton dash meter. I apologize for that. Newton is force, no? Force. Newton is a unit of force. And this one, it's represented in meters. So that's Newton meters, or 12 joules. Okay? So that is for this example. Now, actually, in work in integral calculus, there are various examples, various characteristics, and one of that is work by spring, and that is what I'm going to discuss for you guys. So, an example, a force of 50 pounds is required to hold a spring stretched 5 inches beyond its natural length. How much work is required to stretch it from its natural length to 10 inches beyond its natural length in foot-pounds? Okay, I know this might sound very confusing. So for us not to be confused, let us draw a figure. So we have a spring daw. So spring, let's say for example, this is the spring. Okay. And a spring, no? How much a force is equal to hold a spring stretched 5 inches beyond its natural length. So if this spring, kani siya na spring is stretched 5 inches beyond its natural length, it will look like this na stretch siya, right? So the distance from this point will increase, no? Kasi na stretch na yung spring. So how much work is required to stretch it from its natural length, so from its natural length, which is this one, to 10 inches beyond its natural length in foot-pounds. So 10 inches beyond its natural length, how much work is required? So unsa ka kusgon imong pagbira, no? Para to stretch it, no? 10 inches beyond its natural length. So in this figure 1, the natural length. Figure 2 is we have this force that we exerted, and after stretching this spring here, no, after nato siya na stretch, it will somehow go back, right? So that would be the force also here, pabalik, right? We have two forces when we pull, no, sa atong pagpull, and then pagbalik, there is another force for that one, right? Okay, so the distance from this point, okay, from the original kanisha, the natural length of the spring, to say for example this is the natural length of the spring, to this, up to this point, is what we will call as x. Okay, I hope you understood that one. Again, there's a force here when we pull the spring, and then after nato siya gibira, mubalik siya, and that there is a force in what we call it a restored force. So we now have this formula here. Force is equal to K times X. Okay, so where K is actually the spring constant, in which we are going to find here. So we will find K first, and we can find K by by deriving it with this formula. So K is equal to F over X, in which force and X is given. So force is 50, our X is 5, so therefore we have 10 as our K. No? So F is equal to, which is 10, so 10x. So force in terms of X is equal to 10x. Now we can find the work, no, done with this problem, in which the work is equal to, from A to B, f of x dx. Now what is our limit? What is our lower and upper limits here? So the question is, how much work is required to stretch it from its natural length? So this is our natural length, ito, going to 10 inches beyond its natural length. So therefore, that's from 0 to 10, starting from natural length to 10 inches beyond its natural length. So that's 10 dx. Therefore, that is, if we are going to derive that, that's integrate that, that's 10x, diba? So from 0 to 10, sorry. So that is 10x squared sorry, that should be 10x dx, so that's 10x squared over 2, so that's 5x squared. 10x squared over 2, so 5x squared from 0 to 10. Therefore, that is 5 times 10 squared. 10 squared is 100 times 5, that's 500. Okay, 500. Minus 0 is 500 still. Now, take note that what we got is actually pounds per inches. Pounds times inches, no? The question is to find its work in foot pounds. So what are we going to do? So we are going to convert, of course. Convert the units to foot times pounds. So that's in 1 foot, there are 12 inches. So therefore, that's 500 over 12, or equivalent to 125 foot-pounds. 125 over 3 foot-pounds. Okay? So, let's have example number 5. A force of 60 newtons is required to hold a spring. Again, it's a work by spring na problem. In spring, there are various problems, no? Again, there are various problems in spring, and work by spring is one of them, in which this is what we are discussing. So a force of 60 newtons is required to hold a spring, so another force na 60 newtons, that has been stretched from its natural length of 12 centimeters to 17 centimeters. So its natural length is 12, then it was stretched to 17 centimeters. How much work is done in stretching the spring from 15 centimeters to 20 centimeters? Okay, so this problem, so let's say for example, again, this is a spring, ayan. So, okay, this spring here is from this point to this point. Okay, the natural length of spring is 12 centimeters, no? And it was stretched to 17 centimeters. So, we now have, okay, this is 12 centimeters, and it was stretched 17 centimeters. So, the totality of this point to this point, 17 centimeters. Okay, and from this point to this point, of course, that's 17 minus 12, which is 5 centimeters. Okay, so we have our x here as 5 centimeters. We also have our force, which is 60 newtons. Unlike kanina, the problem is different from this one. Okay, how much work is done in stretching the string? So we have the starting from 15 to 20 centimeter here. It's from its natural length to 10 inches beyond. Okay, so let's try to solve this problem. So again, f is equal to k times x. We're going to find k first. Okay, so the force is 60 equals k times our x, which is this one, the 5 centimeters. Class, the question is how much work is done in stretching the spring from 15 centimeters to 20 centimeters. We are going to convert x into meters para what we get in our final answer is Newton per meter. Kasi Newton is just equivalent to joules. So our x, instead of 5 centimeters, let's change it into 0.05 meters. Kasi if you will not change that, your answer is Newton per centimeters, or Newton centimeters, no? So therefore our k is 60 divided by 0.05, which is 1,200. Okay, then f of x, force in terms of x, is equivalent to k, which is 1,200 times x. Now we have our f of x. Then we can get the work done by that problem. So from a to b, f of x dx. Now, what are our limits here? Okay, so guys, how much work is done in stretching the spring from 15 centimeters, so from this point, to 20 centimeters? So therefore, we are going to subtract 15 to its natural length, which is 12. So 15 natural length, which is 12, so minus. Therefore, that's 15 minus 12 is 3 centimeters, or that's in meters, it's 0.03. And 20 minus its natural length, which is 12 centimeters. Okay, kaya diri man, no? Diri man, 20 na siya. And then, natural length, which is 12. Therefore, that's 0.08 meters. Then, f of x is 1,200 x dx. So, that's 1,200 x squared all over 2. So, that's 600 x squared from 0.03 to 0.08. 600 times 0.08 squared minus 600 times 0.03 squared. So we have our final answer as 33/10, or 3.3 Newton meter, or 3.3 joules. That's our final answer. Okay, so thank you for listening. Hope you have learned something.